I am a PhD student from Wrocław University of Science and Technology, and this beautiful city behind me is Wrocław in Poland, but also my PhD is funded by the French government scholarship, and therefore I'm also affiliated with Université d'Angers in France. So let's move to the topic, which will focus on the linear regression. And in our convention, in this linear regression model, the response vector y will be treated as a product of the design matrix. In most cases, it will be either a fixed design matrix X or the random design matrix, mostly for some asymptotic results at the end. And it will be the product of this design matrix and the vector beta, which will be a notation for a parameter vector, which we want to guess, to estimate, or at least, in fact, we want to extract the essential properties of this vector. So, for example, these properties could be like the sign vector of the vector beta, and from this we would know which of its coordinates are positive, which are negative, and which equal 0. This part seems similar to lasso slope, will be one of the generalizations of lasso. And in most of the cases, we also have to notice the existence of the random noise term, which might have some influence or the estimates. And our goal would be to detect the criteria for which this error wouldn't make too much harm to our guess. We distinguish two cases. One will be the noiseless case, which will be rather the theoretical tool, the tool which would help us to design some proper asymptotic results, which would work in the noisy case, in which epsilon is assumed to be distributed symmetrically and continuously. So the most classical linear regression estimator is an ordinary discourse estimator. It sometimes works, but it's not perfect. For example, when the number of parameters is larger than the data, then either the OLS estimator is assumed to not exist, or at least it is assumed to be not unique. Like it depends on the definition of minimum, if you want to have exactly one minimum of the function, or if we want to have a set of minima. And also, if we have some continuous error, for example, the Gaussian one, then our estimate with probability 1 will consist of p totally mutually pairwise different coordinates. So the complexity, the dimension of our solution will be large, and sometimes it will be just too large. So what can we do? For example, we can perform some penalization, and in this case to the function which we want to minimize. So the square of the L2 norm between the vector y and the product x times b. We want to add a norm, which the norm of the vector b. Which norm? It depends. There are many different choices, and we can also tune this penalizer, for example, to obtain different possible outputs. And we will be interested mostly in the pattern of such vector. It would be a set of essential properties which will be induced by a norm, by a penalizer J. In which sense? In that sense that this pattern would have the same abstract class as the subdifferential of the penalizer. So the set of so two vectors will have the same pattern if and only if they will have the same subdifferential. And in this case, we might also we will also consider the dual of this penalizer J, which will be a strong tool to determine the pattern of the estimate. So the examples of penalized estimators have quite an abundant history. They start at least from 1970s from a rich regression estimator in which the penalizer is the square root of an L2 norm. But the one which allows for a large dimension reduction might be an least absolute shrinkage operator called lasso. It was introduced in 1990s, for example, by Tipshirani, in which the penalizer is an L1 norm. So the sum of absolute values of the vector B with only one unique parameter. And we'll talk about its extension, the sorted L1 penalized estimator. It was introduced in around a decade ago by Małgorzata Bogdan, Eot van den Berg, Chiara Sabatti, Wei Jesu, and Emanuele Candes, in which instead of summing the absolute values of B, we sort the vector of absolute values of coordinates of B, and we penalize the largest absolute value with largest unique parameter, the second largest with the second one, and so on and so on. And this norm will be called a sorted L1 norm because it's almost like an L1 norm, but it's sorted. And when the tuning parameters, the vector of tuning parameters, the tuning vector, if it had all coordinates the same, then we would have just usual L1 norm. And in this way, the slope estimator is well defined both in the low dimensional case, so the case of data being larger than the set of parameters, and in the high dimensional case, so the other way around. If all lambdas would be 0, then we would just have no penalizers. We would have an ordinary least squares estimator. So now we would want to define the slope pattern. As I said before, the vectors having the same slope pattern is the set of vectors having the same subdifferential of the penalizing norm, the slope norm in this case. But we may describe it in a more practical way. So the function being the slope pattern would have integer values, p integer values, which we define by the product of the sign of the coordinate and of the ranking of absolute values of coordinates, but in a set of distinct values and of non-zero values. So if a coordinate equals 0, then the coordinate of the pattern vector would also will also equal 0. If it would be if it's positive, that it will be positive. If it's negative, that it will be negative. So the pattern preserves the signs. It also because of the distinction of values, it also preserves clusters. That said, the sets of coordinates with the same absolute values, and also the ranking between clusters will be preserved. So if we have usual in our vector of parameters, if we have one coordinate having large magnitude than the second one, then this property will be also preserved in the pattern vector. So for example, on the left, we have an 8 and 7-dimensional vector x, where the second value with 1, 0. So this 0 will transfer to 0 is in the second coordinate. Then in the first and third coordinate, we have quite small values, 1.5, and they will transfer to 1 as the smallest non-zero coordinate, and the signs will be preserved. The next cluster will be the cluster of 4th, 5th, and 6th coordinate. The vector of force, it will transfer to plus and minus 2s, and the last, the largest value will be 8. It will transfer to 3. So we know that the vector x had indeed 3 clusters. Okay, so our strong one of our strong tools is the unit ball in the dual of the sorted L1 norm. It's also known as the signed permutahedron. So this is the convex hull of all permutations and all sign changes of the vector lambda. The lambda is the vector of all tuning parameters. So you may see below this ball in the dimension 2 and dimension 3. In larger dimension, it's better to not draw it. It's better to build the intuition gradually. And for example, to compare it with an ordinary squares estimator. Okay, when I write slope versus Olsted, yes, probably the most common answer would be slope is better than OLS and Y, but it's also a bit connected to OLS. The theorems, both for slope and for lasso, state that in the orthogonal design, the difference between both estimators is exactly the orthogonal projection of the ordinary squares estimators into this previous signed permutahedron. And also, when the design is not orthogonal, that we must change a bit the sign permutahedron with respect to the design matrix X. So in practice, it looks a bit like this. So this is the orthogonal design, the dimension 2. And for example, if we consider this red dot on the top left, we have then this is an ordinary squares estimator. The first coordinate is negative, the second one is positive, a bit larger than the first one. So Lasso would just say that they are the first one is negative, second one is positive, but here as the orthogonal projection onto the permutahedron lies into an oblique face, then both coordinates of the difference of the slope vector would be not only the not only consistent of vectors of the same size, but they will be also clusterized. If the difference is too large with respect to lambda, so with respect to this ball, like on below, then we would not have clusterization. And similar methods work also for the non-orthogonal case. In this case, our signed permutahedron and rules of projections are inverted with respect to the matrix, to the design matrix X. Okay, so now we might move for a small amount of time to the asymptotic results. So we have two kinds of asymptotic results. The first one are the results concerning the consistency of the slope estimate. And the second one will concern the strong consistency of the pattern of the slope estimate. And the conditions are different for both results. So in this case, we have the sequence of design matrices with n the amount of data growing and the number of parameters staying the same. And we have a limiting, we have this sign of design matrices converging in some sense to the positive definite matrix C. Therefore, we will have the almost sure consistency of the slope of the sequence of slope estimators, if and only if the lambda vector would be asymptotically smaller than n. But this condition is only one-sided. What happens with the slope pattern? With the slope pattern, we would not only want to have lambda smaller than n, but we also want to have a difference between distinct coordinates of lambda to be large enough in order to detect all clusterizations. So we must have additional assumption even in the orthogonal design case. For a general design, the set of assumptions is a bit more abundant. And the main conclusion is that the pattern of slope would be consistent if and only if the magnitude of the lambda vector with respect of n would be asymptotically smaller than n and larger than the square root of n. If there is still at least some positive amount of time, then I will just move briefly to the applications. Most of the slides are the pictures, so it's not too much left. So the application in the orthogonal design would be the signal denoising. Here, the design matrix is built with respect to the orthogonal trigonometric series. Here, the n is equals 300 and the number of parameters p equals 100. The vector beta has 40 non-zero parameters, so the lasso output would have just 40 different non-zero vectors, but here this vector is special. It consists of only 2 clusters, so it would be nice to have and to use the estimate of beta, which has 2 clusters. It would be easier, and the influence and the impact of noise would be much smaller. So we debias lasso and slope by combining it with the ordinary least squares method. In which sense? For example, for slope, at first we use the slope to obtain the slope pattern. Then from the pattern, we make a reduction of the problem. We reduce the dimension of x. And if we have this shrunk model, then we might perform the least squares estimate of this shrunk estimator. And the mean square error will decrease gradually. In those 4 pictures which illustrated, at first we have ordinary least squares estimator. In second, we have the cross-validated lasso. Later on, bottom left, we have the lasso combined with OLS. So first pattern, then estimation. And at the end, we have the debiased slope. And also, when it comes to the pattern recovery, we might see that on the top we have the support of the vector preserved well, but the coordinates inside the support are different. In slope, we recover also the clusters. So if I move to okay, so then thank you for your attention, and if you want if you are interested in some references, you might see it right here. So
thank you, Tomasz, for this. Sorry, thank you, Tomasz, for this very interesting talk. Are there any questions? So please raise your hand. So I will start with one question. I'm a bit bugged by slope. I mean, in a sense, it hurts my intuition because I use the SCAD quite a lot, and in the SCAD you penalize less the largest coefficients. I mean, the first derivative decreases and then gets actually go to 0 for large enough coefficients. Here, it's exactly, well, it's not exactly, but it's kind of the contrary, because you penalize more the largest coefficient. So do you have an intuition why this works, and why would you do that?
mostly the intuition, at least the geometrical one, would consist on the convexity of such penalizer. I'm not sure if the penalizer in SCAD is also the convex one.
It's not convex, but, yeah.
It's not convex, and here we have the convex penalization. So at least in low dimension, the solution will be unique because we would have a projection onto a convex set. So this is one of some intuitions why to use the convex penalizers, and also this geometrical approach was quite recently extended by us in our paper with Piotr Gracek, Ulrika Schneider, and Patrick Thirtyfel. It's visible on the French version on the HAL, HAL, and it's also visible on arXiv.
Okay, thank you. Yeah, Andrei?
Thank you. It was a very interesting presentation, and I think it opens also some things for the upcoming keynote in a few minutes' time. You mentioned lasso, which was developed by Dipshirani. Could this also be extended instead of slope into some transformation of the general lasso penalization estimator instead of the slope?
So when it comes to use the generalized lasso, we are not focusing too much on the magnitude of coordinates of the vector b, but rather on the positions on this vector b, which might be a very strong tool when we have some prior knowledge about this vector itself. So, for example, if we know that some of the coordinates will have a strong impact and some will be not relevant too much, but if we don't have this knowledge yet, then it would be nice to at least obtain it, and for that reason we might use slope. Like we have some unknown problems, and we have some data, like for example in the blood test, which when the blood can be measured in millions of ways, but we want to obtain an answer which could be interpretable.
Okay, thank you. Thanks.
Sorry. Do I still have the time for one question, Andrei? Okay. So I don't see any other questions. I will ask my question. So I'm kind of amazed by the results you get in the MSc. So when I see the difference of performance with respect to the lasso and to the OLS, do you have an explanation why your performance is so great? Yeah, you can see it in this graph, or you can see it in the last slide, I think. Yeah, if you could comment a little bit on that.
Yes. So in lasso, we just perform one lasso estimation, and one way also see that the red line is always here below the black line, because lasso is the shrinkage estimator, so it will move the solution or at least a bit towards zero. But when it comes to the debiased lasso, we at first use the lasso to obtain the sign vector, and then we might shrink our space, shrink the vector, shrink the design matrix by removing the irrelevant coordinates. So the coordinates which respective coordinates in the lasso estimate would equal 0, and then on the less dimensional space we perform the least squares estimation, and maybe this reduction might be a reason why it works a bit better.